So welcome to my presentation with the title Mechanical Properties and Fracture Behavior of Copper Sheets. My name is Peter Auer and I'm member of the research group of Lightweight Informing Technologies of Graz University Technology. This was a joint project with the industrial company Mark Metallwarenfabrik, also from Austria. I give you a short overview about the content of my presentation. First, I start with our motivation for this project. Then I give you a brief introduction which material we used. Then I come to the experiments we performed. Then I show you our FEM simulations, our models, and then I come to the results with a short summary. What was our motivation for this project? The electrification of the mobility sector will multiply the demand for copper and his alloys in the future. And the industry always focuses on efficient processing of these materials or sheets, especially for cutting, punching, blanking processes. And therefore, FEM simulation becomes more and more important. And this requires reliable material data, especially the elastoplastic behavior and the fracture behavior. Also, we have these processes at room temperature, and they are quasi-static processes. But locally, we saw in our investigations, we have strain rates from quasi-static up to several hundred of strain rate. And also the temperature is locally from room temperature up to several hundred, so 200 degrees. So this is the region where we wanted to determine our material parameters. What was the material we used? We got a commercial oxygen-free high conductivity copper. This means this copper has nearly 100% of copper content. And the strip thickness of this material was 1.6 millimeter. Now I show you which experiments we performed. First, we did this uniaxial tensile test at low strain rates. There we used our Instron E10000 electromechanical testing machine. There we have the possibility to use a convection furnace, and it was possible to perform these tests from room temperature up to 300 degrees. And we tested here strain rates at quasi-static and also at the strain rate of 0.1. And the strain was measured by using a clip gauge directly on the sample here in the furnace. After this, we also performed uniaxial tensile tests at high strain rates. Therefore, we used a split Hopkinson pressure bar. And here it was also possible to heat up the samples, but it was only possible to do the test at room temperature and at 100 degrees. And here we performed tests at around 230 strain rate and very fast tests at 950. Sorry, the videos here don't work, but it's not a problem. The strain was measured by using a DSE system with a high-speed camera. To verify our material model we developed afterwards, we did a custom-made punching tool by ourselves in our Zwick universal testing machine, which has a maximum force of 100 kilonewton. And there it was possible to punch these copper sheets with different temperatures, so also from room temperature up to 300 degrees. These samples which we produced here, we measured afterwards with our optical scanning system from the company Gomboc. And here you see such a part which we produced and measured afterwards. And this is afterwards the comparison with our simulations. Now I come to our simulations. For the material model, we decided to use the Johnson-Cook plasticity model, and for the cracking or for the fracture criterion, we used this normalized Crocross-Lantham criterion. These are the parameters we then optimized and iteratively determined. And the good thing is these parameters are all available in this commercial FEM software D-form, which we used for our simulations. Here you see our the simulation models of our strain, as a tensile test for low strain rate test, and also on the lower side, the smaller sample geometry for the high strain rate tests. And this is our simulation model, a 2D axisymmetric model for the punching test. The punching test was performed in reality and also in simulation with the quasi-adiabatic punching with a velocity of 100 millimeters per second. Okay, I come now to the results. Here you see our measured stress-strain curves. We performed all the tests with 3 repetitions. You see we have for our strain rates always for the lower strain rates, we have for 4 temperatures determined. And for the higher strain rates, we have also 3 repetitions and for these 2 temperatures. Out from these real tests, then we found, we optimized our Johnson-Cook plasticity model. There we saw we had a problem at lower strains because the stresses there in this Johnson-Cook model were too high, and therefore we implemented a correction factor, which you see here, and this adapts our standard Johnson-Cook model to our modified Johnson-Cook model in this region of 0 to 0.2 of strain, and lowers the strain in this region. This was very important, but I let you see this afterwards. Now, these are the results of our modified Johnson-Cook plasticity model. We simulated this strain rate and the high strain rate tests. And you see for a constant temperature, here we have performed the different strain rates. Red is the real test thing, and gray is the simulation, and they are very good comparable, or quite the same. This is always force over displacement. Why is the strain rate here the high strain lower? Yes, because the geometry is smaller and therefore the force is smaller. We have the same diagram here with a constant quasi-static flow, a quasi-static strain rate, and here you see our curves for different temperatures. And so simulation or our plasticity model matches really good the real testing. To compare with the real punching, therefore we did the simulation of the real punching. And you see here also the force over displacement curve from our real test, which is the red color, and the simulation is the curves of our simulation. The gray curve is our simulation. And you see our model is quite good in, or matches very good the real testings. At the end, I want you to give a short, we measured these parts. You see, we made a cross-section through the scanning and compared this with our simulations. Gray is the measured real part. And you see there is a difference to this Johnson-Cook standard model, which we determined, and also with this Johnson-Cook parameters out from literature, there's a difference. And our modified Johnson-Cook model is quite the same like the real measured part. So, short summary, the flow stress of this copper was investigated for strain rates in this region from quasi-static to 1000 and temperature range from room temperature up to 300. The flow curves according to the classical Johnson-Cook plasticity, was iteratively determined by inverse modeling. A modification of the classical Johnson-Cook plasticity was proposed to decrease the flow stress for low plastic strains, to consider this early yielding. And the flow curves were successfully used for FM modeling of the high-speed punching process for these copper sheets. We used a constant fracture parameter for the normalized Korkhoff-Lantham fracture criterion, and this is appropriate for punching simulations. So thank you very much, and I'm open for questions.